This is a survey spectrum measured from PTFE. Quantification has been performed using transmission corrected data. It's used escape depth corrected Scofield cross sections, and there's also a peak model involved where the carbon peak includes a component which is from a CH type material, so either contamination or degraded form of this PTFE sample. And after performing these corrections, we end up with the expected stoichiometry for PTFE. As you can see here, the ratio of the CF peak from the fluorine to the carbon is 2:1. So this is the expected ratio for PTFE. And the fact that we get this ratio deserves explanation, and the explanation of how this has been achieved is the subject of this video. So we'll begin the investigation of quantification of PTFE by looking at a pair of measurements from a Teflon or PTFE sample, where we've either got the neutralizer off or the neutralizer on. And this means that the sample, when the neutralizer is off, can charge. And the consequence of this charging is that the positive charge is attracting the electrons that are leaving the sample, and hence this fluorine 1s peak that is in the neutralized form now appears at about 150 electron volts to lower energy, because the electrons are being attracted back to the sample, so they lose energy as they leave the sample. And this actually is quite a useful test for the quantification, because we can see how the movement of peaks within the kinetic energy range alters the outcome for relative intensity of peaks. And the way we're going to look at this is, first of all, by not quantifying fluorine with respect to carbon, but we'll quantify fluorine with respect to fluorine, because we have two peaks, both of which emanate from fluorine, so they should produce a consistent peak intensity. So let us first of all create a pair of regions and compare these intensities. So there are two annotation labels on these peaks, so I can use create from labels, and this will use the label and also the relative sensitivity factor that is defined by those labels have come in from the element library. So we've got a fluorine RSF for the 1s and the 2s, and these are the scale factors that will change the peak area from the fluorine 1s. So these two should actually appear, once scaled by these relative sensitivity factors, with the same scaled area. So when I put up a quantification table looking at the regions, if these sensitivity factors have worked correctly and these peaks have been measured from fluorine and they are both fluorine, then we ought to get 50-50, and we don't. And we don't get 50-50 because the transmission of the instrument has changed such that the intensity that you see here for the fluorine 2s has been attenuated for some reason with respect to the same signal that's coming from fluorine but appearing from the 1s. Now we can also look at this again, where these same peaks appear in the spectrum. They're a bit distorted by virtue of the fact that the sample is charging and is probably continuing to charge as the measurement is performed. So there are factors why this is not a perfectly fair test, but nevertheless it gives some sort of insight. And again, we'll just create a pair of regions, and again I'll have to adjust the region limits because the peak shape is somewhat distorted here. And we'll do it again for just check this. Let's give it a bit more region here, put up a table, and this time they've come up the other way round. But nevertheless you can see that we've got fluorine 1s. Again, it's increased relative to the fluorine 2s. So between these two measurements, the intensity of this fluorine 1s peak is now more intense relative to the fluorine 2s than the first measurement. Here it was 60 to 40. So So something is wrong with this calculation. Either these relative sensitivity factors are not correct, or these peaks are being changed in intensity due to instrumental effects, which are generally referred to as transmission function. So we can see that these two measurements from the same instrument with slightly, different conditions, neutralizer on, neutralizer off, have produced different ratios for the fluorine 1s to the fluorine 2s. So what happens if we look at a different instrument? This here is PTFE measured from an axis 165, and we've got no transmission in this file. So we've got a survey spectrum, and the survey spectrum has the characteristic shapes that we're seeing. Let's just go to a cascade so we can see these together. You can see that there's the PTFE from the SSI instrument, and there's the PTFE from the axis 165, and again you can see the different peaks here. So let's propagate the region and the annotation from the SSI to this axis 165 data, and then just have a look at the outcome before we decide that this is the final quantification. Let's just adjust the regions and make sure that the regions do make sense on this new set of data. The peaks are slightly narrower, we've got better energy resolution, but nevertheless what we're ending up with is a spectrum. It's got the carbon that you see here, but the fluorine 1s and the fluorine 2s are again showing that we've got a significant difference in the amount of fluorine if we measure it using these relative sensitivity factors and these two peaks. So how do we understand this disparity between the amount of fluorine as measured by these two different photoemission lines? Well, the most obvious difference here is that the fluorine 1s and the fluorine 2s appear at different kinetic energies. That is to say that when the electrons are emitted from the sample, they come off with different kinetic energies which have to be collected by the detector after passing through a lens system and a hemispherical analyzer. So let's have a look at a schematic that illustrates what's happening to these electrons. So this represents a sample, and an image of the sample is transferred at a given kinetic energy through these lenses, which will actually retard the electrons for a given kinetic energy. So we're looking at a fluorine 1s that will require a different retardation than the fluorine 2s, because they're separated by about 700 electron volts. And passing through these lenses, we have to have an image of the sample that will arrive at the hemispherical analyzer, and this image will then be transferred round the hemispherical analyzer, and those electrons of the given pass energy, so if we've set this at 160 electron volt pass energy, that means that all electrons for a given initial kinetic energy must have been retarded so that when they arrive at this point here, they all have 160 electron volts. Otherwise they would hit either the outer hemisphere or the inner hemisphere and not actually arrive at the detector. So the key point is that we have a set of electrons and that represents an image that is formed here, which must ultimately get through to the detector. And what we must have is the image formed here for both the fluorine 1s and the fluorine 2s must be identical if we expect to get peaks, which we can then scale by the Scofield cross sections so that we end up with comparable signal for fluorine once scaled. So how could this go wrong? Well, one possibility is that the lens at one kinetic energy passes through a reduced image, and this reduced image then forms a hot spot on the detector, and so you get a reduced amount of the detector system collecting the signal, so that might cause one peak to attenuate relative to another. Another problem might be that the image is expanding So you no longer have the same image, same size image at the entrance slit, so you're collecting electrons effectively from a smaller area on the sample. So again, that could attenuate the signal relative to this ideal situation where both would appear at the same kinetic energy with the same image size and position. And then the third option is that the image may stay the same size, but it may move. So if the image moves, that too may have an influence on the signal. For example, if the X-ray source does not have a uniform illumination, then potentially you may move, the sample may move, and you may lose some of the illumination, and hence the signal may change yet again. So there are definitely ways that signal can change, and the question is this important in terms of quantification of XPS? If you have a homogeneous sample, then in principle none of these changes alter your ability to quantify your data. And that's because if you can work out what these changes are for your instrument, then you can calculate a transmission function and you can correct the instrument for such artifacts. And there may be other reasons why the signal attenuates or amplifies depending on where you are in the kinetic energy range. But this thought experiment here is a reasonable way of thinking about how signal can change, as we've seen in these data. These data have no transmission correction within the data set. There's no transmission function here, so the only corrections that have been performed are these escape depth Scofield cross-section adjustments to these peak areas, and it's resulted in this difference in the amount of fluorine as measured by these two peaks, because these peaks are separated by a significant kinetic energy difference, and the lens functions behave differently apparently. Nevertheless, we ought to be able to calculate a transmission function that should correct for this. Now, if we look at another example, in this case, this is not PTFE, this is a different material. This is PVDF. It's again fluorine carbon, and the oxygen here is unexpected, but nevertheless the fluorine and the carbon are here, and we have the characteristic fluorine 1s and the fluorine 2s. So let us first of all transfer the quantification regions. So we've calculated the quantification table. Let's close that so we can see it. So we just select the survey spectrum, go back to the spectrum for which the regions are defined, and now right click, and then regions and annotation will be propagated. It's got a different element transition, survey rather than wide. So that's why it gave me that warning message. Nevertheless, it's transferred the region and the annotation table, so we can see that we're getting a different quantification. Let's just check that the peaks are in fact, well, we need some adjustment here. So let's bring up the quantification parameters dialog window, make a shift in that peak, and that needs a little shift too. So we end up with a quantification based on the fluorine 1s and the fluorine 2s, which is much closer to 1:1. And the difference between these data and the previous example of PTFE is that this one has a transmission function as part of the data file. And if you do control page up, you will see this transmission function in the VAMAS file, and you can see that these regions are being adjusted based on this declining signal. So for whatever reason, this transmission for the instrument that measured these data do vary as a function of kinetic energy, and it is a declining signal as a function of kinetic energy that should be expected. So this is the type of result that you achieve when you've properly transmission corrected an axis ultra And this is hybrid mode on an axis ultra, so this is equivalent to the type of measurement that would be performed on an axis 165. So this represents the kind of result when you don't do transmission function correction. And if you go to yet another form of these instruments, what we have here is an axis nova, where the data are being collected in spectroscopy mode using a lens function that is set up for imaging. And the key point here is that we've got an improvement just by actually turning off the standard transmission function that comes with these instruments. If I turn it on, you can see that you get something that looks close to the axis 165, and that's because the transmission function is relative to the hybrid mode on an axis ultra instrument. And so by using these Scofield cross sections and the normal Kratos transmission correction, you end up with a poorer quantification than if you don't use the transmission at all. So let's have a look at why that's the case. And what you see here are images that have been acquired in the same mode as the spectrum for the PTFE. And I'm looking at two images that are roughly have kinetic energy that is equivalent to the Fluorine 1s and the Fluorine 2s. And you can see that they don't overlay. They're very close. You can see the yellow indicates there's a correlation of signal. The red would correspond to the Fluorine 1s. So you can see there's some kind of movement here. And you can also see there's a slight difference in size. But nevertheless, it's not too extreme. And the reason that you're getting an improvement over the basic axis 165 without any transmission correction, just by using these Scofield cross sections, is that these images really are doing a reasonable job of filling the slot, and they don't move too much. So this improvement in the quantification between these two fluorine peaks seems to have occurred because of the imaging quality of this lens mode. So the question really arises, what happens if you actually intend to fully calibrate the images that are passing from the sample into the analyzer? And this is exactly what this experiment is showing. We've got, again, the Fluorine 1s, the Fluorine 2s, and I've overlaid these images, and this mode has been very carefully set up so we get good image registration, and the quality of the image is also good throughout the energy range. So actually, if I go up, you can see that what happens is, for the most part, the images align very nicely over an interval that would be equivalent to that Fluorine 1s and 2s. And what happens at low kinetic energy is that the images start to move. So apart from at low kinetic energy, we have very stable and well-formed images, and these images are being passed into the analyzer when we do spectroscopy. So this is now an image of the slot that is used in the spectroscopic mode that would be used to acquire spectra. And as I go down this, you can see that the slot is again matching very nicely with the full image, and apart from slightly poorer spatial resolution, we've got exactly the same properties. So once again, let's just look at what the Fluorine 1s and the Fluorine 2s should look like. And again, we've got lots of yellow here showing good correlation. Image size is good, positioned good. We really have quite a nicely set up instrument once we've seen these types of images at the entrance slit to the hemispherical analyzer. So what does this do for spectra? And here we have spectra that have been taken in spectroscopic mode through the deflection analyzer, and these are from gold, and this one is from copper. And you can see that the copper 3p and the copper 2p are both very close, and similarly you've got very close between the S. These are quantified using Scofield cross-sections corrected for escape depth, and that was gold under the same conditions. So the only one that shows a real deviation is perhaps the gold 4F, but that's a very intense peak and difficult to actually define what the background should look like. But generally they have been scaled by these Scofield cross-sections, escape depth corrected, and produced comparable intensities over this range of kinetic energies. And this range of kinetic energies is very much the type of range that we're talking about for the fluorine. So if I put up the fluorine markers, you can see that over this range of peaks it's equivalent to what we're looking at with the Fluorine 1s and the Fluorine 2s. So how can we use this? Well, if we've got a spectrum that is behaving as if it has a flat transmission, which is what this appears to be doing, then we can use this to correct other spectra. Given this gold spectrum that's been measured from a lens mode for which we have a flat response, so the transmission function is almost flat, that's the implication of being able to quantify these peaks across this gold spectrum, and also for the copper. We've got a wide energy range, and we're getting a reasonable quantification using these Scofield cross-sections that have been corrected for escape depth. Well, we can make use of this if we compare it to other modes of the same instrument for which the transmission isn't necessarily flat. So if I go here and select this particular file, what I've got here is a file containing a set of survey measurements from different operating modes, and you can see that the shape of the spectrum changes. It's not just the resolution of the peaks, the backgrounds alter. So these have different transmission characteristics, and these pass energy 80 field of view 1 are all measurements from the mode that was used to collect the PTFE data that we've been looking at. So what I'm going to do now is I'm going to go back to my ideal measurement, and I'm going to take a copy of this spectrum. Now actually I have another one that has a wider energy range that was acquired under the same conditions. So if I take this spectrum and I go to the spectrum processing dialog window and I select the calculator, I can make this the operand. So what I've done is I've loaded this spectrum and I can now use that in a calculation. So what we will do is we'll go back to these spectra here that are overlaid. If I select these spectra and I say divide, and then I can take the operand, this is the ideal spectrum, and I'm going to divide these three pass energy 80 spectra by this operand. So if you ignore the strangeness that happens at the low kinetic and high kinetic energies, that's due to low signal above the valence band, so we get very similar responses from these three spectra when we divide by the ideal spectrum. So I'll just select one of these, and what I'm going to do is create, using a background type, a smooth form from this data by using a polynomial regression background type, and I'm going to use a value of 6. So we'll use a polynomial of degree 5, that's 6 parameters to adjust, and you can see that you get a smooth curve here that goes through the data, and you can see that there are also some anomalies in and around about where the peaks are, so there is a certain element of uncertainty here, but you have a general trend here that shows that field of view 1 pass energy 80 does appear to decline in intensity as a function of kinetic energy increasing. So let's now use another function, which is on the test data tab. I'll say replace by envelope. So what I've done is I've got a section of this spectrum where, or rather this ratioed spectrum, where I've replaced the data by this background type that was a polynomial that was fitted to the data, and it's an interval that is defined by a region, and I can now create from a region using this option on the Sims toolbar, spectra from regions. So I will press this button and I end up with a VAMAS block that contains a curve that is hopefully representative of the difference between the transmission of field of view 1 pass energy 80 and the ideal spectrum that we measured using the well-calibrated image dataset. So let's first of all make sure that I've calculated an appropriate range for the fluorine. And this is the bit that I'm worried about. Note we have a curve here that includes the fluorine 2s, so I'm quite happy with that now. So let's take this and we'll load this into the calculator. So I've said set operand, and you can see that it's turned a beige color. That indicates that it's been loaded correctly. So what I would like to do now is go back to the spectrum for which I had some improvement when I took off the transmission function, and what I'd like to do is add to this spectrum the transmission function that has been calculated from that gold spectrum. So if I go to intensity calibrate, there's this new option that says update TF with calc operand. So the calculator operand that I loaded was the ratioed spectrum, and that's giving me the characteristics of the transmission for the field of view 1 pass energy 80, and those are the operating modes that were used to acquire these data. And if I now say apply, what happens is that I do control page up, and you now see that the operand has been loaded as the transmission function as best it can over the energy range that was available. So here we have the fluorine 1s and the fluorine 2s are both within this range of the transmission. You can see that actually it's still in a state where we are not using any transmission at all. But if I now add the transmission to the calculation, lo and behold, the ratio of the fluorine 1s to the fluorine 2s has turned out to be very close to 1:1. So what we've done is we've measured a spectrum in a mode that is not ideal. It's reasonably good, but not ideal. We've created an ideal spectrum, and from that we've created a response function relative to this ideal spectrum for this field of view 1, pass energy 80, and I'm now getting results that suggest that we have a very good chance of obtaining a good quantification from fluorine 1s, fluorine 2s, and when we apply this to this carbon, we should get a good quantification for PTFE. Finally, we'll have a look at data that were acquired using field of view 2, pass energy 160 and the slot mode that have been measured from PTFE directly. So when we look at the survey spectrum, we can quantify this survey spectrum and do this based on the fluorine 1s and the carbon 1s. So when I say create regions, we get a pair of regions, and these regions have been set up. Let me just clear down these element markers. We've got a quantification that is not the stoichiometry that you'd expect, but the reason for that is that we've still got the transmission function active that came in from the instrument. So this is correcting these data so they are looking more like hybrid mode of an Axis Ultra. But if we turn this off and press update, you see that you get actually remarkably accurate stoichiometry. That's 2 to 1.